Hi, good morning. So this was the work I did with Norimiki while we're still at, I was still at Disney Research and he was at CMU. It's a little bit old, so I hope I will remember everything. So the title is Representing and Manipulating Mesh-Based Character Animations. So this is one of the few papers here about animation. So animation for human subjects, as we all know, is still time-consuming and complex and still expensive. So it takes a lot of time for animators to create a character animation for movies and games and etc. So some of the problems related to this is the way people do it. So the traditional framework for character animation is to use a surface mesh as well as a underlying skeleton. So and the way it works is that as you see in the image there, so you have a surface mesh representing your character and you have a skeleton underlining that that mesh. And the way it works is that we need to animate the skeleton by assigning motion parameters to the joints, and the geometry in the skeleton are then connected by skinning. So you have like many steps if you want to really animate this character. So in reality, what you would wish is a method or a way to animate the character directly from video. So you have someone performing in front of video, and then you have a corresponding performance or animation. So, but as you can imagine, both methods are still complex. And this work here tries to, again, bridge a gap between both techniques. So people in the past, they start to see this problem with skeletal-based animation, and they developed some mesh-based techniques that would forget about all the kinematic skeleton underlying the surface, and they would work directly on the mesh. So one of the first methods was the one by Samla and Popovich, the deformation transfer, where they could transfer the deformation from one input mesh sequence to another one. So if you see characters or human characters, Jonathan Stark and Adrian Hilton, they also developed some methods to animate some characters directly from video without any underlying skeleton. So this brings us to another method, the one we developed and presented at CEGRAPI 2008, which was the performance capture method, where you could directly from video animate a character without any kinematic information. So, and after that, many other methods are being developed to also try to bridge this gap and try to improve the whole animation process. However, we still have some problems when you're dealing with mesh animations. So although it's easier to create, it is still hard to edit and especially to reuse the animations. So as soon as you capture something, it's really hard to change it. So as you can imagine, if you want to change a mesh-based animation, you need to change each vertex for each frame of the animation, which is really hard. So this brings to our method. So if you think about a mesh-based representation for character animation, it is a really good representation because it allows us a lot of flexibility during the animation creation. So you're not bounded to the skeleton constraint. So you can, in the same format, in the same representation, capture both coarse and fine animations, for instance, the animation of the skin, cloth, and etc., using the same representation. On the other hand, it's still complex to be edited or manipulated. So, and at this point is the one that I want to try to attack with this paper. So, and since it's hard to edit and manipulate, a mesh-based representation for character animation is really hard to be integrated into the conventional animation pipeline. So, I don't know if you worked with animators before, they are really picky people, so they really like to change things and they really like to have the animation in the way they want. So it would be really hard for an animator to actually capture something or have a data and work it directly. So it will change something. So we need to provide tools for the animators to work and to change the data in the way they want. Of course, this is not the first paper trying to work and trying to improve and convert a mesh-based representation. There has been a lot of approaches trying to represent mesh animations using skeletal-based representations. So one of them, it's again my paper at Eurographics 2008, where giving a mesh-based representation, we converted this mesh-based representation into a skeletal-based representation. But my approach and many other approaches in the literature up to now, they cannot preserve the time-varying details in the animation. For instance, when you know skinning, so when you are presenting a complex animation, mesh-based animation with skinning, you are losing some details. These are details I call time-varying details. For instance, the motion of the skirt, or the motion of cloth, or the skin, and etc. So when I say a mesh animation, I'm saying a sequence of triangle mesh models, so with the same connectivity over time. So this is the input to this method. And in the way you try to partially solve this problem is by using a hybrid representation. So you try to divide a mesh-based representation into a coarse and a fine mesh component. So the coarse representation can be automatically fitted using a kinematic structure. So giving the input, a mesh sequence, you can automatically input a kinematic skeleton to it. And this will allow us to represent and reproduce the input animation as close as possible. But still we are losing some details. This matches the conventional skeleton-based paradigm, which means that with the coarse representation, you are able to give the animators a data they can use, but you are still losing some details. So the details then are which I call fine deformations, which are pretty much the motion-dependent time-varying details of the animation. And in this case, to be able to learn these animations from the input, we decided to use a nonlinear approach, which is the GPLVM. So it's Gaussian process that I will talk briefly in the future. So first about the coarse deformations. So here we're not doing a lot of new stuff. You're just redoing what was done already in 2008. So actually we're simplifying a little bit that method. So you are automatically feeding a non-human-like kinematic skeleton to the input mesh model. So we know it's a human, you know how many bones it has, how is the hierarchy, and etc. So after feeding this skeleton to the input, you can then, considering the whole sequence, you can calculate the joint parameters and the blending skinning weights, such that the coarse representation will then reproduce the input animation as close as possible. So again, this matches the conventional skeleton-based paradigm, which is good for the animators. So briefly, how this works. So giving a input mesh animation, which is a sequence of mesh models, we first apply a spectral clustering approach to segment this mesh sequence actually. So this spectral clustering approach, you then we will create parts in the model that corresponds to the body parts. So this uses the idea that body parts, so parts of the body that belongs together, they will move more or less in the same way. So after doing the segmentation, we can then find the joins between the underlying body part segments. So when given the joins, you can then, since you know the hierarchy, you know it's a human, we can then create the skeleton that will match this mesh model. So then, and in the end, we can, using a known approach, we can calculate the skinning weights that will then match, that will make our skinning representation match the input. So again, this was already done. I'm just reproducing what I done there, and as as we see in the results, we cannot, with this approach, we cannot still reproduce the non-rigid time-varying details, because you're only getting like the average model for every frame. You're not being able to get the important details, time-varying details. So this is more or less the main point in this paper, is how you model defined details. So to do this, we use a probabilistic nonlinear formulation. So the idea behind it is that the underlying subspace of defined deformations is inherently, oh, this is hard. It's more or less nonlinear. This word is hard. Which means that we probably cannot find a linear formulation that will be able to represent all these details that you have when, for instance, cloth is waving, or when the skin is moving. So which means we are representing the time varying details as a function. We should be able to relate both components. We decided to represent the time varying details, so the details on the surface, as a function of the underlying skeleton motion. So this is really nice because it allows us to easily generate different configurations for the skeleton. And when you generate different configurations for the skeleton, we can then create the according deformations. This is also good because it simplifies the editing process. So animators can now directly work on what they know, which is the underlying skeleton, and the corresponding time varying details on the surface will be reconstructed during the editing operations. So Gaussian, we'll be using Gaussian process latent variable models, which is a nice machine learning formulation, and you can think about it for the ones who don't know it as a nonlinear dimensionality technique to compactly represent information, in this case deformations. So we use it because it's really robust and it can generalize well from a small, is this my mic? It can robustly generalize from a small set of data, and it does not tend to overfit as many other approaches would do. And it's also widely used for learning human motion. It's also used to model large dimensional data, such as silhouettes, voxel data, and even simple deformation models. So it has been used before in the literature, and it proved to be quite well. So I'll quickly give an introduction to Gaussian process. Of course, the focus here is not to go into too much detail on this. There's a lot of literature there, a lot of details on the paper. So imagine you have a set of data points, and you don't know if these points are real, if they belong to something real, or if they're just noise or outliers. So how can you find out which function this data comes from? So this is a problem you have it almost every time, and without making some assumptions, it's really hard to find a function that can match these points, and it can find out which ones are outliers and which ones are not. So Gaussian process, they come in handy because they are a nice way to represent this prior information on functions. So you can then have some nice assumptions about how this function will look like. And it has a lot of applications. So it has applications on classification, optimization, and regression, etc. So the one that you are interested here is pretty much the application of regression. So, okay, and just to give an idea what can be done with Gaussian process, the general idea is if you have a set of training points T that corresponds to input value X, so Gaussian process can help you to predict what is the new value T giving a new input X. So it's pretty much what the idea behind Gaussian process, and it can do this because it has this prior information on the functions. So the focus here is not Gaussian process. We use some extensions on Gaussian process. The Gaussian process is a huge theory, so we use some extensions which are the GP LVM. So in this case, you are using the Gaussian process to you're using it to model high-dimensional data into a low-dimensional latent space. So we can think about GPLVM as extension of linear PCA. So it's pretty much you have a data which is really high-dimensional, and you don't want to deal with this huge amount of data, and GPLVM can help you to compact and to compress this data into a small number of values. Again, it has been used for human motion before because it generalizes well from small data sets. It can be used to generate new motion sequences, which is also nice. So it's able to extrapolate a little bit from the data as well. It's very flexible, and it creates natural looking solutions. So we, as an extension of Gaussian process as well, you have a sort of partner for GPLVM, which is the GPDM, which additionally in this low dimensional space, this latent space, it learns dynamics. So it's able to distinguish. Is this coming from my mic? Okay. GPDM also it's able to learn the dynamics in this latent low dimensional space, which is also good. But coming back to define deformations in our approach, so here I will be, I'm sorry for the mathematicians here, I will be extremely superficial on the way I will go with Gaussian process and GPLVM. If you want to learn more, there are more details on the paper, there are more details on the literature. I only have 4 minutes left, so I need to go briefly on the idea. So our goal here is to encode the time-varying details of the input mesh animation using the joint parameters. So in a sense, given the theta, the joint parameters, and d, the mesh details you want to find, you want to find the function f that then will be able to correlate joint parameters and details. So in our case, the time-varying details are the difference is the difference between the input mesh animation and its corresponding skinned mesh model representation. So this whole idea here is to find the function f. So unfortunately, you cannot directly find this function f. So we need to go into some steps to be able to find this relationship. So what you do is you link the skeletal motion, which are the joint parameters, to define deformations using GPLVM using this low dimensional space. So we create an additional space, which you call latent space X, and you do the mapping there. So in this case, you need to find 2 additional functions. One that brings us from the joint parameters space to this low dimensional space, and another one that brings us from the high dimensional space constructed by the time-varying details to the low dimensional space, latent low dimensional space. So in this low dimensional space, if you don't care about how we're constructing this space, a given joint angle might correspond to multiple surface details. So if you don't care about it, so if you imagine someone's walking and if you stop that sequence, so if you don't care about speed, that particular and unique sequence might have different representations depending on many properties. So GPDM, which is an additional technique based on Gaussian process, allows us to properly model the situation by enforcing dynamics on this low dimensional representation. So, which means we'll be taking an improved latent space by mapping the data with similar details but different motions to different variables. So visually, you'll have something like this. If you want to reconstruct defined deformations, so the animator changes the joint parameters. So giving theta, we will be using the function fs of x. We'll be using the inverse to find the place on the latent space where this value x lies. And in the second step, when you have x, you can then find the details using the forward mapping fm of x. So you then are able to, using this whole formulation, to giving a new set of joint parameters to find the corresponding, the best match for the details. So again, this is really a small and quick overview on Gaussian process and GPLVM. Nice equations, and more details are on the paper if you want. And at the end, we are able to convert the mesh animation by first creating the coarse deformation using the estimated joint parameter theta and the skinning weight, resulting in a skin model. Thereafter, we can use theta, actually use theta and theta in the previous frame because we are dealing with dynamics, to calculate the corresponding time variant details. And we sum up both terms to create the final representation. So quickly for the results. So we test our approach in many sequences from the publicly available methods, animations varying from walking, marching, fighting. The input mesh animations, they vary from 5,000 vertices to 10 million vertices. There we also explain a multi-resolution technique that allows us to deal with this high amount of data. And animations are quite short. They vary from 70 to 400 frames, which is pretty much what people are capturing right now with performance capture methods. So you performed a few experiments. The first one is pretty much to test the efficiency of systems design. So one could just think why you are not using the vertex position directly and not only this difference between the mesh and the skinning result. So we find out that if you're using this, there is some correlation between this small details that you have, and this enables our approach to work much better. So as you can see in the graph, if you try to use the full deformations, the error is quite large and it varies a lot. So we cannot, which means that you cannot generalize well to different input configurations. So if you see a single frame and you compare our hybrid solution and the skinning result, you can see, especially on the skirt, you can see that our approach represents much better the input in comparison to skinning. So skinning is not able to really capture these details. This can be seen also in a graph where and in blue you can see the error of our hybrid representation in to reconstruct an input sequence in comparison to the skinning result, which is much higher. Quickly about the running time. So it's GPLVM has some drawbacks. One of them is speed. So it takes some time to train this model. But the nice thing is that the editing operations can be done in real time. Additionally, you also found out some nice properties in terms of compression. So you could compress a mesh-based animation using this approach. So here you can see a few examples of some editing operations. You could change some motions on the arms, torso, and the head, and the resulting animation was still looking okay. We could also do something new, which would be modify proportions on the input mesh animation. So you could do some sort of retargeting, direct retargeting. So you could change the size of torso and changing the legs, and our approach would be able to handle it nicely. So I had a video, but I don't have time. Of course, our method is not perfect. We still have a lot of limitations. So our approach is targeted to kinematically based subjects. So if you want to use it to something that does not look like human, it will not work. We cannot edit the time varying details. So they need to be reconstructed based on the motion underlying skeleton. Of course, our level of editing is limited. You cannot handle motions, and you cannot perform editings that are too far from what was learned in the beginning. And you have some problems with scalability, and this comes from the GPLVM, which means that as soon as you start to increase the number of samples, the processing time is exponential, so it becomes really, really complex. But we can solve it by using cyclic motions, as many people in animation do. So to conclude, this is pretty much one of the new approaches there to try to solve this problem, which is to convert a mesh-based character animation into this new hybrid representation that's more flexible for editing purposes, and it can be integrated in the animation pipeline. So the main focus here is pretty much this how we are able to learn, find deformations using a nonlinear approach and integrate it to what animators are used to have. So thank you very much for attention. Sorry for getting to a little bit more of the time. So you're free to send me emails if you want. I'm sort of alone in Espírito Santo in computer graphics, so feel free to come visit if you want as well. Thank you.
Thanks, Adilson. Questions? Well, we have a question that inspired one. Let's talk about the way you target find the level. How do you do that?
So the nice thing about this whole approach when you're targeting is that you are able to since you converted this mesh-based representation into a new skeleton-based representation, so if you're able to sort of glue the joints to underline the joints to the surface, and then it's pretty much I think I use the mean value coordinates to do that. So then when you change the skeleton, you are automatically changing the surface as well. And since the joints defined details do not care about the joint dimensions, they care much more about the angles, you're able to reconstruct the details there as well.
So you didn't go into much detail about the kind of editing you're able to do, because you start from a motion captured sequence and then you edit that, or you just create a whole new animation from scratch. Can you do that?
So this method starts with this mesh animation, right? So
this was captured, right?
Yeah, this needs to be captured by it's not the same as motion capture, right? Because motion capture captures only the angles, right? In this case, you are capturing the whole thing. We cannot do something completely new. So if you have a sequence of someone walking, you cannot, with that data, you cannot make someone jump, for instance.
Okay, that's what I wanted.